Hey class, and welcome back to the second half of Chapter 6, Section 1, where we're tackling different questions about how water works in gardens. So the next question I had for you, question 3, why does water pour gently out of an open hose but comes rushing out of an open faucet? So thinking about what we just discovered in the last video, what do you think? Well, ultimately it's because that hose has a longer distance over which energy can be wasted. Those viscous forces, that internal friction within the fluid, has the opportunity to waste energy. And as we notice, the smaller the diameter, the much more rapidly energy is able to be lost. So if you notice, in cities, they have huge pipes that take water to different neighborhoods and so on. Very little energy is going to be lost in those massive pipes. But once it gets into your hose or into your house and you get much smaller diameters, energy can be wasted much more rapidly. Imagine like a drip system where you have 1/4 inch diameter. Those are really, really small little hoses. Those can waste energy much more rapidly. Not dissimilar from the example we saw when we did the water tower demonstration in class last week. So again, water is being wasted, and where does it go? It actually turns into thermal energy. So as your water gets slowed down by viscosity in your hose, it actually slightly heats up just a little bit as a result. So again, different things affect the rate at which viscous forces take energy away, but it definitely gets affected by the size of the diameter. The faster the flow is going, the greater the pressure difference, the stronger the overall effect is, kind of like air resistance in that regard as well. So let's now look at the next question. How does water spray fast from a nozzle? So how do nozzles work? That's ultimately what we're looking at here, right? So on question 6, I asked you this exact question. Here's a little picture, over here is a little picture of a nozzle, right? How does this narrowing create faster moving water? And I have another picture of that coming up in a second, but that's what we were asked here. What did you put? Well, what happens is that narrowing, the restriction of the water, causes regions where the pressure is going to increase. There's almost like a traffic jam of water trying to move through there. And as the pressure increases at that traffic jam, it's going to cause the water to speed up as it moves through. So again, there's a pressure imbalance that's created by the nozzle accelerating the water through there, causing it to come out faster at the other end after you've reduced the overall size. So if you look here, right, what we have in this nozzle, up here where the water is more spread out, you have kind of medium speed water with a medium amount of pressure. As it narrows, what you're going to have is over here, you have a region where the water, in order to make it through, has to speed up in that narrowing. So you get regions of high pressure building up, accelerating the water towards the lower pressure. Because again, things move from high pressure to low pressure, right? The traffic jam, just like it does with driving, creates high pressure. In driving, it creates high blood pressure. But anyway, the traffic jam creates higher pressure, and so then the water will accelerate through. So again, it's ultimately about a pressure imbalance creating the higher speed water, because things always want to move from high pressure to low pressure. Okay? Now, thinking about the same idea, how does a bend in a pipe work? That's the next question on here, the last one, number 7, right? How does a bend work? Well, like, okay, yeah, sure, it bends, so the water has to bend. But what makes it bend? If you think the water's moving straight and then it just slams into the end and then bounces off and turns, is that what happens? If it did, you think a lot of energy would be wasted in every single bend. Well, maybe that happens a little bit, but again, it's ultimately about pressure difference. How do we make fluids move? Pressure difference. How do we make fluids accelerate? Pressure difference. How do we make them speed up? Pressure difference. How do we make them turn? Pressure difference, okay? So there's this pressure imbalance. And you think about it, as the water comes up, as it's going to or would be potentially slamming into this outer edge, that would create a region where the water has to slow down and therefore increase in pressure, just like Bernoulli told us. So the speed goes down, the pressure goes up on the outside. On the inside, the water's kind of almost rushing by that inside corner. So you get, again, higher speed here and lower pressure as a result. Again, same as Bernoulli's principle. So you get high pressure on the outside curve, low pressure on the inside. That's a pressure imbalance, pressure difference. The water will accelerate from the outside towards the inside, and it turns. Again, high pressure to low pressure causes that overall turn to occur. Pretty neat, right? Physics is everywhere. So the fifth question we just have two more, right? What causes hissing sounds? I don't know if you've ever noticed, but like if you just barely turn on a faucet, there's a lot of noise. It sounds like it's almost like gurgling or bubbling, like there's water, or excuse me, air mixed in with your water, which isn't exactly the case, right? So what causes that noise? Well, it's actually caused by something known as turbulence or chaotic flow, which we've talked a little bit about already. We'll address it much more in the next section, but it's caused by turbulence or chaotic flow, and chaotic flow generates noise. So what we've been talking about so far, like in those last couple pictures with nice, straight, streamlined flow, nice, straight, streamlined flow is what we call laminar. Like, again, picture like a laminated piece of paper. It's nice and smooth, right? Laminar flow is nice and smooth, steady flow. Now we need to talk a little bit about when we don't have nice, steady flow, and that's what we call turbulence or chaotic flow. All right, so turbulence is where you can really burn through and lose a lot of energy in a fluid, is because of chaotic flow, things not moving in the same direction as one another. They rub against each other much more. Because if you think about water moving in a pipe, if all the water is moving together in this exact same direction at a steady speed, there's almost no friction between the water, only a little bit at the very edge. But if you have water that's kind of tumbling, like imagine rapids in a river, then you're going to have a lot of water moving in all different directions, and that's where you're going to have a lot of energy being lost as a result. So to just kind of give you pictures to visualize this idea of laminar versus turbulent flow. Here's kind of a picture to show laminar flow, nice, steady, everything's moving in the same direction, maybe some slight variations in speed due to viscous forces on the edge. But turbulent flow is when things are much more chaotic and moving in different directions relative to one another. All right, so again, here's kind of showing airflow over airplane wing or around a ball or something, right? You'll have nice steady laminar flow on the sides and in front, but you'll have turbulent flow back behind your object because of the disturbance, all right? And you can see this. I mean, just go and stick a stick in a river or something. You'll see turbulence produced behind it. I do it with the creek in the backyard sometimes. It's fun to see physics all the time, you know? Except Gus isn't that receptive to my lessons, but I try to teach him. So how do we determine whether something is turbulent or not, whether the flow, the chaotic flow, is enough to call it turbulent versus laminar? Well, ultimately, it's challenging, right? It depends. Okay, you can have things where the inertia, the desire for things to want to keep moving in the same direction, sort of dominates. Or you can have things where the viscous forces, the friction within the fluid, keeps it all moving in the same steady direction, right? So what happens is, if the bottom of that wins, so if your number is on the smaller side, known as the Reynolds number, if it's on the smaller side, then you have laminar flow because the viscosity is keeping everything in the same line, kind of rubbing and moving together in the same direction. If the inertia wins, if you have too many pieces of fluid moving in different directions, it's so chaotic that we consider it to be turbulent. So now engineers and scientists have kind of worked together to figure out, all right, what are kind of general areas in which we can consider flow to be more or less laminar versus more or less turbulent. So what they decided is, if you have a Reynolds number, again, if you calculate this value and you get a Reynolds number that's below 2,300, then they say overall it's laminar. The motion of the water is generally together. And then if you calculate it and you find that your Reynolds number is above 2,300, then that means that there's too much chaos in the flow and you're going to have turbulent flow. Again, if you get way below that, then it's much more laminar. If you get way over it, it's going to be much more chaotic. But they kind of had to draw the line in the sand and say, all right, here's what we're going to sort of determine as the boundary between laminar and turbulent. And so they picked 2,300 as the value for that. And some people say, well, what happens if it's exactly 2,300? And in reality, in science, nothing's ever exactly 2,300, right? It's going to be like 2,300.001, or it's going to be 2,999.99999, right? Or I guess 2,399. I added an extra number in there because I'm weird. Anyway, so does that make sense? Again, above that value, turbulent; below 2,300, laminar. So here's an example for us to look at. Let's imagine that we have a trout, a fish, that has a width of 10 centimeters And it wants to know, apparently it asked you, I don't know, it's a curious trout. It wants to know how fast it can swim to avoid causing turbulence. It doesn't want to be wasting energy and doesn't want to be causing ripples that predators might be able to see and detect it. Have you ever seen a trout in a river, by the way? You should check it out or try to. It's amazingly difficult. They're kind of interesting looking back, makes them blend in so well under the water. It's super hard to pick them out from above. Anyway, so what do you think? How would you figure out how fast this fish can go while still maintaining non-turbulent flow? Give it a try. Pause the video. All right, so hopefully you tried to solve this one. Let's give it a go. So the Reynolds number is calculated by looking at the density multiplied by the length, multiplied by the speed, and then divided by the viscosity. So if we want to figure out the speed, the V here, right, how fast it can move, I can multiply my viscosity the other side, divide by density, and then divide by the length. So the speed that it can move would be equal to the Reynolds number times the viscosity divided by the density multiplied by the length. So we can plug in. Now, if you notice, I didn't tell you what Reynolds number to put, but he wants to know how fast he can swim just before producing turbulence. And so I put in, for the Reynolds number, 2,300, that border right before it changes the type of flow. Multiply that by the viscosity, and then divide by the density and the length, and we should find that he can swim at 0.023 meters per second. So not very fast, really, before causing turbulence. All right, so the final question I had for you, why do pipes rattle when you close a faucet? You should try this. If you haven't done it, try it. Turn on your faucet so that it's open and it's able to flow as fastly as possible, and then very rapidly shut the faucet off. And you'll notice something known as a water hammer. The water will actually slam against the end of your faucet as soon as you close it. It's really quite interesting. So why is that? What causes that rattle, that hit from the water? Well, ultimately, it's because water has mass. It's moving with some velocity, so therefore it must have momentum. The water carries with it a certain amount of momentum, and that momentum causes it to hit whatever is closing it at the faucet. So water, just like with any other mass that's moving, can transfer its momentum via an impulse. Again, if you remember before, right, momentum was equal to, or change in momentum was equal to your impulse, which was a force times time. So just in case you don't remember this, right, impulse was change in momentum, and your change in momentum was equal to your average net force, your average force acting on something, multiplied by the change in time. So a force exerted over some time caused a change in momentum, or anytime we had a change in momentum, we knew that there is some force being applied over some period of time. And so now we can have a change in momentum caused by water as well slamming into an object. All right. But again, with water, with fluids, right, we're not talking about forces as often. Instead, we're more concerned about pressure and so on, right? So how do you think we quantify the impulse for a fluid? Well, I'll tell you. It's actually about the pressure and the surface area and the time. So again, force times time is how we quantified impulse before, but now we want pressure times area, which if you remember, pressure is just force over area. So it's the exact same thing. Again, I don't want you getting confused with this, but if you remember, right, pressure, now don't get confused, this P here is momentum, this P here is pressure, but pressure was equal to force divided by surface area. And so if we're taking pressure and multiplying it by surface area, the surface area would cancel and you just get the force. So it's really not a new equation. It's the same equation, just written in terms of different variables. But anyway, so moving water will slam into the end of your faucet and generate an impulse as it loses its momentum. So it's applying a force to the end of the line to your faucet, and that's why it rattles and shakes a little bit. So you should try that for sure. So this is really the kind of introduction to garden watering and the physics involved that I wanted to give you all. We'll talk more about this idea of fluids and how they move in the next section of Chapter 6 as well, but we're going to call that a box-worthy day. So talk to you all next time.